back to 1955. Hi, so what we have here is a Survey Radiac No.2, which I saw advertised as untested on eBay. It was wrongly described as a Geiger counter, but we'll get onto that in a bit. I paid £34 for it and £5 postage. In the listing it says that it belonged to a Radio Ham, who unfortunately is no longer with us. It was made by a company called EK Coal Limited, and it came in its original box and PVC haversack, complete with small screwdriver and service sheet. It seems quite an early unit, this one, with it having a serial number of just over 2000. I've seen pictures of others on the internet where the serial number's over 34,000, so they must have made quite a few of these. They were used by the British military and the Royal Observer Corps until around 1982, and they would be used in the event of a radiological incident such as a nuclear war or accident to check for levels of radioactivity in the area. Looking at the service sheet, this one seems to be last serviced in 1987. I mean, it's a beautifully made piece of kit. It's very robust and solid. We've got a switch on the side there, which is for off, battery test, on with lamp and on. And if we turn it, it actually mechanically moves a little metal piece here to indicate whether it's on or off. 1950s technology, yeah? And also we've got a switch here, which is for to set the range of it. And when you turn that, you'll actually see this dial here mechanically move, just like so. And then we've got the higher range, and that's the set 0, which is done by this potentiometer here. Now, this takes 4 batteries, which aren't readily available anymore. I did see one online, but they were under about £30 for a battery, which I thought was a bit excessive. It normally takes 2 D cells. One's for the meter illumination here, which has got a little bulb in the side, and one for the heater for the triode valve, or tube for our American friends, which is inside, which acts like an amplifier from the ion chamber that picks up the radiation, and that's what makes the meter move. And the batteries, we've got a 9V supply for the anode of the triode and a 30V supply for the grid bias voltage, but we'll get into a circuit diagram that a bit later on. So I think what we'll do is we'll get into it, we'll have a look, we'll see if there's anything wrong with it, because like I said, it's just untested. But it'll be interesting to have a look inside of it, I think. But I think the first problem I'm going to have is some of these Allen bolts here appear to be rounded off. So we'll just try removing some of them. Right, well, that one's loosened off. So that's one of them. Let's try this one. Right, so we've got those 2 loosened off. But I'm fairly sure the rest of them won't budge. They're actually rounded off. So I think we might have to take this over the workshop, get it on the pillar drill, and we'll see if we can drill these out, which is a bit of a shame. But I think that's the only way we'll be able to get into it, unfortunately. Right, we'll head over to the workshop. Right, I think that's them all out, and resume. Right, so I think the first thing we'll do is we'll have a look at this battery compartment. So this is where the 2 standard D-type cells go, just in here and here. And like I said, one powers the illumination and the other one powers the heater for the triode valve or tube that's inside. And this section here is where we've got the 9V battery that goes between these 2 spiky points here. And to fit it, you just undo this and it moves apart like that. And this is where the 30 volt battery goes, between here and here. So I think I might have a cunning solution to that, but we'll come to that a bit later on in the video. Right, let's see if we can get this part out now then. I managed to get all the screws out and we didn't damage the casing, so that's good. I'll have to see if I can get some replacement screws to go in there. Now this has got a gasket around the outside because the ion chamber sensitivity is affected by moisture. So why this is a sealed unit is to try and keep the moisture out of it. And what we've got down here, I'll just put this down a sec, is a little vial that contains some silica beads, which is a desiccant, and that's supposed to be blue. And if it's pink, it means the desiccant is fully absorbed as much as it can, so that desiccant will be needing replaced. And there's the illumination bulb for the display. Right, I'll just put this to one side and let's have a look at this part. I'll zoom down a bit. So I'll just find something to point with. So what we've got here, this is the triode valve or tube here, which acts as the amplifier. And this part here is the ion chamber, which detects the radiation. And it looks like we've got a few resistors here, which I'm not sure what those are for. They'll be for some kind of bias or whatever for the different ranges possibly. We've got a spring here. That must be the mechanical linkage for the on-off display. Let's see how that works. Yeah, so we can see it moves and that lever there, and at the same time it changes the contacts on this part here. And at the bottom we've got the range selector. So if I turn that one, I mightn't be to see that from this angle. Let's have a look from here, see if we can see any better. Yeah, we can see that moves a lever down here, just down there, which then selects the different display range on the dial. So overall there's not really a lot in here. Let's have a look under this compartment here. Let's get a different screwdriver. Well, this one fits. And it's slightly smaller one. And I see there's always one. Let's try this screwdriver. Let's just scroll down a little bit. So there's the vacuum tube there, which acts as the amplifier. And then we've got 3 precision resistors here, which are enclosed in glass. I presume that's to keep the resistance stable, and so it's not affected from any outside things like moisture or anything like that, or variations in temperature possibly even, I don't know. So this is 1.7 times 10 to the power 8th ohms, whatever that works out at. I'll let you leave it in the comments. 1.5 times 10 to the power 9 and 1.5 times 10 to the power 10 ohms. Yeah, maths wasn't one of my very strong points, let's say. So that's about it really. There's not really too much else in it. I've got 2 potentiometers here. One is for the user to be able to set 0 And I think the other one is a calibration one, which is used by the factory to calibrate it. All of the cable management here with the, I forgot what that's called, it's like wire wrap sort of stuff around it, isn't it? So I wonder if we can actually get it to work. This is the ion chamber here, which when I've had a look at ion chambers, it's pretty much nothing more than a can with an electrode inside. I actually found some pictures online of where you can actually make your own radiation detector out of a tin can. I'll just bring a couple of pictures up so you can have a look. So here's one of them here, where you can see they've just used a tin can and a transistor and a multimeter and built a radiation detector. So I did find a circuit diagram for one of these types of meters, or a simplified circuit diagram. So I'll bring that up on the screen so we can see how it works. So if we look here, this is the ionization chamber, and that goes to the grid of the triode valve. We can see the range resistors here change the voltage going to the grid, and this chamber bias battery here, that's the 30 volt one. The anode battery, that'll be the 9 volt one, and the heater cell here is the 1.5D cell. So the only battery that's missing off here is the light for the meter. And then we've just got a few auxiliary resistors around the place just for bias and things and whatever. So overall, not really a very complicated circuit. But I just thought it'd be interesting for you to have a look so you could figure out and see exactly how the circuit works. Right, I'm just going to pop the screws back in on this part. Hopefully without damaging anything. It's got a little bit of foam there which holds the resistors and the triode safely. There's a number or something there. I'm not sure what that says. It looks like 2167. Is that the serial number of it? I'll have to have a look at the other part. Yes, 2167. So that's the actual serial number of the unit written on there as well. Right, let's zoom back out a bit. So let's see if we can come up with some way of making this work, and then hopefully let's see if we can find a way of testing it as well, just to see if it works. Now I'm not sure how feasible that's going to be, but you know, we might have to just get a bit creative with that. Right, let's see how we're going to power this thing up then. Well, the D cells, that isn't a problem. But we need to come up with some method of supplying 9 volts and 30 volts. That'll fit nicely in there, because I don't really want to alter this too much. I'd rather try and keep it original. It just seems a bit of a shame to, you know, start butchering it and adding extra bits in and stuff and whatever. So I might try and see if I can keep this as original as possible. Right, I'll have a little bit think on this and see if I can come up with something. So I did manage to find the original operator's handbook for this on Internet Archive. So we'll just scroll down a little bit here, and you can see the typewriter typed font there. Function, description, let's go down a little bit. So there's some nice illustrations of the unit there with the satchel and the actual unit in front of it. And a little bit telling you about the function of it. And a brief circuit description. So it says the current collected in the ionization chamber is measured by means of a single electrometer valve circuit. This indicating meter is connected to the cathode circuit of this valve, and the standing current corresponding to zero ionization chamber current is backed off, so the meter reads zero deflection. The valve current is adjusted by varying the grid bias, and the preset control that performs this function is known as the set zero control. A further preset control provides for the adjustment for the sensitivity of the electrometer stage, or electrometer stage. This is known as the calibration control. And here it describes the batteries and the different purposes of the different batteries. And about the desiccator. So I might actually have a look at that, see if we can dry it out or replace it. I'm sure I've got some silica gel from some other things that have arrived before that I might be able to replace it with. Haversack assembly, just telling you about a little haversack there. Just telling you about the controls again with a nice illustration. And you can actually operate it from within the haversack because the side flap opens, which I thought was a nice little touch. This part here, we'll actually have a look at that. So this beta window, what happens with that is you can close it and it limits the amount of beta radiation that the ionization chamber will detect. So it'll only pick up gamma radiation. And this part is for changing the filament and lamp cells, which are the D cells that I mentioned earlier. Here, battery B3 and battery B4 should be replaced when the voltage is 27 volts or below. And that's a picture of how the batteries are connected. And that's pretty much it from the manual. I thought it was quite nice to see a 1950s manual preserved on Internet Archive. Right, so I've had a little bit to think about this and how we're going to do this to power this up. So I've got a 9-volt battery. However, the 9-volt battery is supposed to fit in this section here. And it's too big. But it will fit where the 30-volt battery is supposed to go. And what we can do, we can just tack the wires onto here and onto here. So that's that one covered. Now the problem is the 30-volt battery. So I was thinking, how can we get 30 volts from a battery? So what I had the idea of was some CR2032s. And if we get 5 of them, put them together like this with some tape, we should be able to fit a stack of them here, like that, and another stack of them just next to them like that. And then we can link them together and maybe use the spot welder or something, and that'll give us our 30 volts that we can then run a wire down to this terminal here. And that should be the 9 volts and the 30 volts covered. And the 1.5 volts are just standard D cells, which I have. So I think that's what I'm going to try. Right, so I've just finished taping these batteries together. So I've got a stack of 5 here and a stack of 5 there. Obviously we've got positive here, negative there. So I've got one of these metal strips here that I'm going to use the little spot welder just to spot weld on. So we'll give this a go. Well, that seemed to be quite successful. Right, let's see. 32 volts, that'll do. Right, so I think I'll use a bit more of this strip. We'll tag a little bit on here so I can solder a wire to, and a little bit here, and then I'll encase it in tape, and that should give us our 30 volts. So I've just finished soldering up a couple of these little tin things here. So let's spot weld those on. We'll do the same with the positive one. Excellent. Right, just cover that in tape now, I think. There we go, 130 volt battery pack. Right, I'll get the spot welder out of the way. Right, so the negative of the 9 volts needs to go to this contact here. So I'm just going to see if I can put a little bit of solder just on the end of it. There we go. tin these wires first, and I might just cut them down a little bit. Right, so those two secured. So that should go there like that, and we'll secure it with some tape or something. So now we need to wire up the 30 volts, which hopefully should fit somewhere like that. I might need a little bit extra space on this. I might have to wind that screw back a fraction. Perhaps might want to solder that first. I wonder if it's better going on the side of this. I think it's just sucking all the heat out of the iron. Well, it's on. And it's a bit warm. Right, so the positive side of the 30 volts needs to go to this terminal here. So we'll just cut that a bit shorter. And the negative side needs to go to here. Yeah, I think we'll get away with that if I put some tape around that just to hold everything together. I think that should fit in. Right, let's see what we get on these terminals. So we should have 9 volts one way and minus 30 the other. So let's have a look. Right, so minus 32, and we should have plus 9 here, and we do. Nice. Let's get rid of some of this off my bench here. I'll just zoom out a fraction. Let's have a look at the desiccant part. And let's have a look at this gamma window. So the desiccant part is here. Now I'm not sure whether I've got a screwdriver or anything big enough. Let's try these. Right, let's have a look at that, see if we can figure out how this bit works. See if we can move this little window. Looks like we've got a little gasket in there. I'm not sure whether these are actually used as serviceable or whether you just throw them away. It's actually got some more threads on the back of it. Let's have a look. I wonder if you could just dry this out, possibly. Maybe bake it for a while, see if it will dry it out. That's the only thing I can think. And it doesn't look like this bit of paper's reusable. I mean, I can try baking that as well, see if it changes colour. Right, I'll give that a go, and then we'll come back and see exactly what happened, if anything. Well, I've tried drying the desiccant out for a couple of hours. The pink things haven't turned blue, but the vial thing does actually rattle now. I think you can hear there. So, I'm just going to have to put this back together as is for now. If I remember how this went. Yeah, that bit went in there. And those two discs went in here. Right, I think this little hole here might be for to test the unit by putting maybe a radioactive sample in or something. I'm not 100%. That's the only thing I could think that could be for, because that goes directly to where the into the ionisation chamber here through this hole. So I think that might be for testing or calibration. You know, if you've got a radioactive substance, you place it in there, and that's how you actually calibrate the unit. Right, let's have a look at this gamma plate. Let's see if this will come off. Or if these are seized in as well. Oh, they seem to come off nice and easy. That's good. Oh, that came off a bit severe. So this is actually shielded at the moment. If we want it to pick up beta radiation, we need to open this flap like that, and that will allow the particles in through this window here. So I think I'll leave it in that configuration. Right, so that's how that works. Let's pop this back on. Right, let's get this bit and see if these batteries work. So there's my Franken battery. Let's see if it fits in. Yes, I'll just knock the rubber bit off. Right, so that's that. And I think what we'll do, I'll switch that off. We'll just put these batteries in like that instead of unscrewing the covers. Right, so I wonder if it actually does anything now. Let's try it. Let's switch it on. Well, that's the battery test. So on with the lamp, and it's immediately gone below the 0. I'll switch it off there, you can see it's actually on the 0. So I think we need to set the 0 first. So if we do that, and then we'll try this button, this adjuster here. There we go. So this actually seems to be working. Yeah, because when I touch the front here, it is actually moving. Right, let's put it back off a moment. And we'll go on to the lowest scale. That's the battery test. And that's on with the lamp. Well, it doesn't actually seem to be on 0 still there. Let's just give this a little tweak. Right, there we go. Right, it is actually. So we know the valve's working because it's actually amplifying my finger there. Now, have I got a radioactive source? I do think I have. One moment, please. And resume. And what I've got here is a uranium glass marble, which it mightn't actually be enough to trigger this, but we'll see. And I've got my UV light here, and as you can see, the uranium glass fluoresces under UV light. I actually bought this for when I built my internet connected Geiger counter. In fact, I'll just grab that, you can have a look, which is this device here. And this connects to the internet. I think it's every 240 seconds. I'll just reset it and hopefully it'll spring to life. I'll tell you what, I'll just zoom down a little bit so you can see. And it connects to Wi-Fi with this ESP8266. It might get a high reading because we've got a, it's actually saying 0 at the moment. There we go. So it's showing 12 counts per minute at the minute, and you can see the little light flashing there. And if I put this next to it, that'll probably go berserk a bit, I think. There we go, 42, 60. 132. I'll just reset that so it doesn't actually send the data to the site. So yeah, so I built this a while back, and there's a site called Radmon that it sends the data to, which there's quite a few users around the world. So if there's ever a radiological event, or you think there's something not quite right and there's radioactivity or rumours of radioactivity or bombs going off somewhere, have a look on Radmon. Right, let's put this away now. So let's see if this has any effect on this. I would say not really. I'll just zoom back out a bit. Actually looks like it's going the other way. Actually looks like it's making the needle go down, not up. I'll just make sure this is on 0. I mean, obviously with it having moisture in the air here as well, that's a factor. That'll skew results. Oh, possibly a little bit there. It's a bit hard to tell. I'm not just sure if it's moving in the air that's doing it here. It could just be movement of the air and moisture that's actually doing that. Not the actual radioactivity from the marble. And I'll have to see if I can get some replacement screws for the ones that I've had to drill, unfortunately. But overall I think it's a nice looking piece of kit and a piece of history that's worth preserving. I mean, what do you think? Let me know in the comments below. So I think we might have to get a little bit creative, because obviously I haven't got any large radioactive sources and I don't want the authorities knocking at my door, so we might have to kind of simulate a real world test on this. I don't know, but I'm sure I'll come up with something.
Now for step 1, you need to cut the...
Which one, sorry? Was it red or brown?
You need to cut...
I think you said brown. Right, here goes. I wish Vince was here.